We now talk about how to use some numerical methods to approximate the definite integrals. Our target is to approximate the definite integral of a function f of x from a to b. To simplify, we assume the function is always positive. By that we mean the graph of the function is above the horizontal axis. Now let's recall geometrically the definite integral of a function from a to b is represented by the area under the graph of the function when x is from a to b. The area under the red curve. To use the trapezoid rule, the first thing we do is to divide the interval from a to b into n subintervals of equal width. We use delta of x to denote the width of the subintervals, and we use x0, x1, up to xn to denote the partition points. On this sketch, you have a particular case that n value is equal to 6. We divide the interval from a to b into 6 subintervals. Now, the idea is to use the sum of the areas of many trapezoids to approximate the area under the graph of the function from a to b. Intuitively, you see the approximation will work. Now, let's look into some details. For instance, the trapezoid on the far left is determined by the subinterval from x0 to x1. Actually, the trapezoid is formed by 4 points. This point, x0 on the horizontal axis, x1 on the horizontal axis, and also these 2 points on the graph of the function, on the curve. Now look at the mouse cursor. This point has the height of this point is the value of the function at x0, and the height of this point is the value of the function at x1. Now let's recall the formula for computing the area of a trapezoid. It's easy to see the area of the trapezoid is computed using the first term on the right hand side. And likewise, each subinterval will determine a trapezoid, and every trapezoid has an area. So the sum of the areas of all the trapezoids is given by the right hand side of this equation. It can also be simplified to the following form, the form on the next line. This is called the famous trapezoid rule. Additionally, it's possible to estimate the error using this formula. It's called the formula for the error bound. It's denoted by ET, T for trapezoid, E for error. Okay. We do not prove the formula, but we'll illustrate how to use the formula to estimate the error. Any estimation is useless if you do not know how to estimate the error. The second numerical method for approximating the definite integrals is called the seamstress rule. I had a typo in here, so there's only one rule, of course. To use the seamstress rule, the first thing we do is to divide the interval into n subintervals of equal width. There's a restriction on n. N has to be even. You are going to see why very shortly. On this sketch, you have a particular case that n value is equal to 6. Now, the idea is to use the sum of the areas of under many parabolas to approximate the area under the graph of the function from a to b. I will repeat. The idea is to use the sum of the areas under many parabolas to approximate the area under the graph of the function from a to b, which is the definite integral of the function from a to b. I'll make some more comments. Starting from the far left endpoint x0, every 3 consecutive points determines a unique parabola. Now, for instance, there's a unique parabola determined by x0, x1, and x2. There's a unique parabola determined by x2, x3, and x4. And likewise, there's one and only one parabola determined by the 3 points x4, x5, and x6. For instance, the parabola determined by x4, x5, and x6 is the parabola passing through the 3 points on the graph of the function. This point has x-coordinate of x4 and y-coordinate, the value of the function at x4, f of x4, right? And this point, you look at the mouse cursor, this point has x-coordinate of x5 and the y-coordinate is the value of the function at x5. And likewise, this point has x-coordinate of x6 and y-coordinate of f of x6. We just mentioned earlier, there's a unique parabola determined by these 3 points. Actually, it can be proved the area under the parabola determined by these 3 points is given by 1/3 of the width of the subinterval times the value of the function at x4, f of x4, and then plus 4 times the value of the function at x5, and then plus the value of the function at x6. This will give you a typical term on this line. You look at the mouse cursor. Actually, when n value is equal to 6, this will give you the last term in here. Now, the formula can be simplified to the following form. The following form is the famous Simpson's rule. Also, there's a formula for estimating the error bound. The error bound for the Simpson's rule is given by that formula. We'll illustrate how to use the formula to estimate the error. Now it's time to work on some questions. You look at question 1 on the screen. In this question, we are going to use the trapezoid rule with n value of 3 to approximate the integral from 0 to 6 of that function, x times e to the power of negative x over 2. N value of 3, it means we divide the interval from 0 to 6 into 3 subintervals of equal width. 2 steps. Now step 1, divide the interval from 0 to 6 into 3 subintervals. of equal width. To use the trapezoid rule formula, we need the width of the subintervals. We also need the partition points. We identify the partition points first. The partition points are, we use x0 to denote the far left point, the far left end point. x0 is 0. You'll see the partition points are 0, 2, 4, and 6. We divide the interval from 0 to 6 into 3 subintervals of equal width. x1 is the next partition point, so which is 2. And then x2 is 4. And then x3 equals 6, the right end point. We also need the width of the subintervals. The width of the subinterval is denoted using the delta of x. In this particular case, the width is 2, of course. After identifying all the numbers we need in the formula, then step 2, the integral we are trying to approximate from 0 to 6, x times e to the power of negative x over 2, that integral is approximated using the trapezoid rule. I will recall the formula. The formula for the trapezoid rule is here. We use that form, okay. Half of the width of the subintervals, and then the value of the function at x0, then plus the value of the function at the right end point, f of xn, and then plus the values of the function at other partition points multiplied by 2. There's a factor of 2 involved in here, so don't forget. Okay. So the formula, we'll copy the formula, okay? You have half of the width of the subintervals, and then the value of the function at x0, the left end point, and then plus the value of the function at x3, which is the value of the function at the right end point of the interval, and then plus 2 times the value of the function at other partition points. We mean at x1 and at x2. 2 times the value of the function at x1, and then plus 2 times the value of the function at x2. That is a copy of the trapezoid rule formula in this particular case. Now we are going to plug in the numbers. Delta of x is equal to 1. Delta of x, the width of the subintervals, is equal to 2. So we have 2 over 2 in here. And then times x0 is 0, the value of the function at 0. Then plus 2 times the value of the function at x1 value is 2, right? And then plus 2 times the value of the function at x2. x2 value is 4. The value of the function at 4. And the last term is the value of the function at 6. x3 value is 6, right? Now the function, we use the definition of the function. The function is x times e to the power of negative half of x. So we have 2 over 2. The value of the function at 0 is equal to 0 times, you replace x value with 0 in the function, right? 0 times e to the power of negative 0 over 2. That's my 0. And then plus 2 times the value of the function at 2 is 2 e to the power of negative 2 over 2. And then plus 2 times the value of the function at 4 is 4 times e to the power of negative 4 over 2. One more term. And then plus the last term is a term without the factor of 2. The last term is the value of the function at 6. So you have 6 times e to the power of negative 6 over 2. Okay. Now enter everything into your calculator. You are going to have the answer. You look at that's my calculator. On the left hand side you have 2 over 2. So this 2 is the width of the subinterval, right? The first term is the value of the function at 0. The second term is 2 times the value of the function at 2, and so on. The next term is 2 times the value of the function at 4. The last term is the value of the function at 6. You enter everything into your calculator. You have the answer. The answer is 2.85 something. It's hard for me to remember. I'm not going to write the answer into the PowerPoint. You just copy the answer into your notes. That's question 1. Now we work on another question. You look at question 2 on the screen. This time we are going to use the seamstress rule with n value of 4 to approximate the same integral. The integral from 0 to 6. The function is x times e to the power of negative half of x. The first thing we do is the same as before. We divide the interval from 0 to 6 into 4 subintervals this time. Because we are going to use n value of 4, it means we divide the interval into 4 subintervals. To use the seamstress rule, we need to identify the partition points. We need to identify the width of the subinterval. Now, the partition points are, we divide the interval from 0 to 6 into 4 subintervals. 6 divided by 4 equals 1.5. So the partition points are the far left endpoint, x0, 0 of course. And then the next partition point, x1, is 1.5. And the x2 is equal to 3. 3 is here. Then x3 is 4.5. And the x4 is equal to 6. So we have identified all the partition points. We divide the interval into 4 subintervals. There should be 5 partition points, right? 1, 2, 3, 4, 5. We also need to identify the width of the subinterval. Also, we have the width of the subinterval is 1.5. 6 divided by 4 is 1.5. It's delta of x. Now we are ready to apply the seamstress rule. The basic formula is here. You have the width of the subinterval divided by 3, and then inside the brackets, you look at the pattern. The first term is the value of the function at the left endpoint, x0. The last term is the value of the function at the right endpoint, f of xn. For all the terms in between, the coefficients are alternating between 4 and 2. You see 4 times the value of the function at x1 plus 2 times the value of the function at x2. The next term would be 4 times the value of the function at x3. Anyway, 4 and 2, the factors are alternating. And then you have the values of the function at x1, at x2, and so on. Okay. We'll apply the formula to this particular question. The integral from 0 to 6 x times e to the power of negative half of x. Now it's approximated by using the seamstress rule. You have the width of the subintervals divided by 3, and then inside the brackets, the first term is the value of the function at x0. The last term is the value of the function at the right endpoint, so which is x4 in this case. And then for all the terms in between, there's a factor for 2 alternating involved. This term would be is 4 times the value of the function at x1, and then plus 2 times the value of the function at x2, and then plus 4 times the value of the function at x3. And then plus the very last term, which is the value of the function at x4. This is the formula of the seamstress rule for this particular case. We have all the numbers we need for this formula. Delta of x is 1.5, and then the x0 is 0, so we have the first term, the value of the function at 0, and then plus 4 times x1, 4 times the value of the function at 1.5, and then plus 2 times the value of the function at 3. x2 value is 3, and then plus 4 times the value of the function at x3. x3 value is 4.5, and then plus the last term, the value of the function at x4, which is the value of the function at 6. Now, for this particular function, we are going to evaluate 1.5 over 3. The value of the function at 0 is, now you look at the function is here. is x times e to the power of negative half of x. So the value of the function at 0 is equal to 0 times e to the power of negative 0 over 2. And then plus 4 times the value of the function at 1.5, and then times e to the power of negative 1.5 over 2. The underlined is the value of the function at 1.5. And then plus 2 times the value of the function at 3. 3 times e to the power of negative 3 over 2. Then plus 4 times the value of the function at 4.5, which is 4.5 e to the power of negative 4.5 over 2. One more term. The last term is the value of the function at 6. So you have 6 times e to the power of negative 6 over 2. That's everything. Now enter everything like that into your calculator. I will show you the answer. Okay. At the beginning, you have the width of the subinterval is 1.5. The width divided by 3 times this term is the value of the function at 0. This term, the highlighted, is the value of the function at 1.5. There's a factor of 4 involved in here. 4 times the value of the function at 1.5. Now the highlighted, that term is the value of the function at 3. There's a factor of 2 involved in here. And you keep on going. That's 4 times the value of the function at 4.5. And then the last term is the value of the function at 6. You enter everything into the formula. You have the answer. I'm not going to write the answer into the PowerPoint. There are too many digits. You just copy the answer onto your notes. That's question 2. Now, question number 3. The question has 2 parts. The first part is to use the trapezoid rule with n value of 10 to approximate the same integral. We just increase the number of subintervals to 10. The second part is to use that formula to estimate the error, to determine the error bound. For the first part, I wrote a little R program. Now you look at the screen. In the program, X is a vector consisting of all the partition points. If you type X and enter, you see all the partition points. This is the left endpoint of the interval from 0 to 6. That's x0. That's x10, which is the right endpoint of the interval. All the numbers in between are other partition points. This line is the definition of the function. The function is x times e to the power of negative half of x. This highlighted line is the formula for the trapezoid. you have half of the width of the subintervals and then times the value of the function at x0 and then 2 times the value of the function at x1, the second partition point, and so on. The answer to the estimation in fraction is that number. Convert the fraction to a decimal number. The answer to the first part of the question is 3.17 something. For the second part of the question, we are going to estimate an error bound. We are going to use this formula to estimate the error. In this formula, we need a value of k. Now look at k. K can be taken as any upper bound of the absolute value of the double derivative of the function on the interval from 0 to 6. Now it's easy to get the second derivative and the triple derivative. You look at the function. We can use the product rule to get the derivative of the function. Simplify the derivative, and then using the product rule again, simplify, and again we can get these two functions, the double derivative and the triple derivative. Now we treat the double derivative to be a function defined on the closed interval from 0 to 6. You see, the function is continuous on the closed interval from 0 to 6 and differentiable on the open interval from 0 to 6. So the absolute maximum and absolute minimum of this function must occur at one of the two endpoints, 0 or 6, or at a critical number of the function. A critical number of a function is a value of x where the triple derivative is equal to 0. But the triple derivative is equal to 0 at only x value of 6. So because this factor is always positive. This means the absolute maximum and absolute minimum of this function must occur at one of the two endpoints, either 0 or 6. And then evaluate the function at 0, evaluate the function at 6. The larger one is the absolute maximum. The smaller one is the absolute minimum. And then you consider the absolute value of this function. So it's easy to see. I'm going to write it down. It is easy to see. I told you why. That the absolute value of the double derivative turns its absolute maximum on the interval from 0 to 6 at x value of 0. Which means that the absolute value of the double derivative is always less than or equal to the value of that function at x value of 0. You plug 0 into the function, into that function, the double derivative. You see the absolute value of this function at x value of 0 is equal to 1. So because e to the power of 0 is equal to 1, and inside the absolute value you have negative 1. It's equal to the absolute value of negative 1, so which is 1. Which means we can take 1 to be the value of k. Now we are ready to estimate the error bound. So we take k value of 1, we just mentioned, and in the formula we need the value of b. The value of b is the upper limit of the integral, so which is 6. We need the value of a, which is the lower limit of the integral, so which is 0. And the value of n is equal to 10. So we are ready to estimate the error. So the error ET, the error for the trapezoidal, is less than or equal to the value of k is 1, and 6 minus 0 to the cubed to the power of 3, and on denominator you have 12 times 10, n value is 10 squared. Now put everything into your calculator. You have the value 0.18. This number is equal to 0.18. Now the meaning of this number. This number means the difference between the actual value of the integral and the approximated value of the integral using the trapezoidal rule with n value of 10. The difference between two values is not more than 0.18. Now question number 4. The question has two parts. The first part is to use the seamstress rule with n value of 10 to approximate the same integral. The second part is to estimate the error using that formula. For the first part, look at our program. X is a vector consisting of all the partition points. We divide the interval from 0 to 6 into 10 subintervals. We have all the partition points on this list. And then this line is the definition of the function. The next line is the formula for the seamstress rule. You see it's 1/3 times the width of the interval, the width of the subintervals, and then the value of the function at the first partition point, 4 times the value of the function at the second partition point, and these coefficients are alternating between 4, 2, 4, 2, and so on. And the last term is the value of the function at the right endpoint, the last partition point. The answer in fraction form is that number, and in decimal form is that number. We now determine an error bound. The formula we use is this one. In the formula, we have a value of m involved. The value of m is any upper bound of the absolute value of the first derivative of the function on the interval from 0 to 6. So we need to get the fourth and the fifth derivatives of the function. To get this, you use the product rule to differentiate the original function, getting the derivative of the function. Simplify using the product rule again, and again, and again. You can get these two functions, the fourth and the fifth derivatives of the function. Now, using very similar arguments to those in question 3, we can see the absolute value of the fourth derivative of the function atteins its maximum when x is equal to 0. The value of this function at x value of 0 is negative 1/2. So this inequality is valid. We use the decimal form to estimate the error. By this we mean we can take m value to be 0.5. M value is 0.5. Now the value of b, I will write everything down. Now we have m value of 0.5, we have b value of 6, we have a value of 0, and we have n value of 10. These are all the numbers we need in this formula. So the error, the absolute value of the error using the seamstress rule is less than or equal to 180 times 10 to the power of 4 on denominator. On numerator you have 0.5 times 6 minus 0, the whole thing to the power of 5. Enter everything into your calculator. This value is 0.00216. 0.00216. Again, the interpretation of this number is as follows. The difference between the actual value of the definite integral and the estimated value of that using the seamstress rule, the difference between the two values is not more than 0.00216. This estimation is pretty good. The next question is in the nature of determining the value of n, the number of subintervals for a given accuracy. We'll work only on question 2. For question 2, you want the error to be less than or equal to 0.001. This is the accuracy you want. So what we are looking for is the value of n, the least number of subintervals needed to achieve that. The formula to estimate the error is here. So we know the value of m is 0.5. We know the value of b. We know the value of a. We are looking for a value of n. We are given the accuracy 0.001. So all we need is to solve the following inequality for n. Solve the following inequality for n. So m value is equal to 0.5, we know that, and b value is 6, a value is 0, the whole thing to the power of 5. On denominator you have 180 times n to the power of 4. So you want this number to be less than or equal to 0.001. This inequality is equivalent to 0.5 times 6 to the power of 5 over 180 times 0.001. Less than or equal to n to the power of 4. You multiply two sides of the inequality by n to the power of 4, and then you divide two sides of the inequality by 0.001. You can achieve that. This means the value of n is greater than or equal to fourth root of this number of 0.5 times 6 to the power of 5 over 180 times 0.001. Put everything into your calculator. This value is 12.1 something. This number is approximated by 12.1 something. Now let's recall, to use the seamstress rule, the value of n has to be an even number. So we are looking for the least even number greater than or equal to 12.1. Now since n is even, so the least possible value of n we can take is n value of 14. The smallest even number greater than 12.1. Now a more precise interpretation, I'm going to state the interpretation. Listen to me carefully. In order the difference between the actual value of the integral and the approximated value of the integral using the seamstress rule, in order the difference is not more than 0.001, the least number of n needed is 14. This means you need to divide the subinterval, you need to divide the interval from 0 to 6 into at least 14 subintervals to achieve that accuracy.